The SR-71 Blackbird, faster than missiles. The spy plane that couldn't be caught. Speed was life, and no aircraft took it more seriously. Fast enough to outrun missiles, high enough to touch space. So secret its existence was denied for years. This is the SR-71 Blackbird, the fastest jet ever built. Imagine this. You're a pilot at 85,000 feet, 16 miles above Earth. The sky above is black. Below, you can see the curvature of the planet. Your windscreen is hot enough to fry an egg. And when enemy missiles launch toward you, your survival depends on one thing: going faster. This isn't science fiction. This was a Tuesday for SR-71 pilots. Today, we're diving deep into the most extraordinary aircraft ever built. A plane so advanced that even after retirement, many of its capabilities remain classified. A machine that redefined what was possible. The crisis that started it all. On May 1st, 1960, the Cold War turned hot in the skies over Soviet territory. CIA pilot Francis Gary Powers was flying his U-2 spy plane at 70,000 feet when a Soviet S-75 Divina surface-to-air missile exploded nearby. Shrapnel tore through the aircraft. Powers barely escaped with his life, parachuting into enemy hands. The incident was a geopolitical disaster. President Eisenhower initially denied the U-2's existence, claiming it was a weather research aircraft that strayed off course. Then the Soviets produced Powers alive and talking. The lie collapsed. The summit with Khrushchev fell apart. America's premier spy platform was exposed as vulnerable. The CIA and Air Force faced a terrifying reality. The Soviets could now reach our reconnaissance aircraft. The U-2 had been untouchable, flying higher than any interceptor or missile. Not anymore. Soviet technology had caught up, and it would only get better. The question became urgent. How do you spy on an enemy that can shoot you down? The answer came from a legendary figure named Clarence Kelly Johnson and his team at Lockheed's Advanced Development Projects Division, better known as the Skunk Works. Johnson's philosophy was radical. If you can't hide from missiles, outrun them. Don't build a plane that flies high. Build one that flies impossibly fast. The requirement was ambitious to the point of insanity. Mach 3 plus speed, 80,000 foot plus altitude, transcontinental range, and radar cross-section small enough to complicate enemy targeting. Oh, and it needed to be operational within a few years. What emerged would rewrite the rules of aviation. The Titanium Challenge. To understand why the SR-71 was revolutionary, you need to understand the problem of speed. At Mach 3, over 2,200 miles per hour, air friction creates tremendous heat. The leading edges of the aircraft reach 900 degrees Fahrenheit. The fuselage averages 500 degrees. This isn't just hot, this is metal melting hot. Aluminum, the standard aircraft material, melts at 1,200 degrees and loses structural strength long before that. Steel warps and becomes brittle under thermal cycling. Traditional materials simply couldn't survive. Kelly Johnson's team needed titanium. Not just some titanium, 85% of the aircraft's structure would need to be titanium alloy. There was just one problem. In the early 1960s, almost nobody knew how to work with titanium at this scale. Here's where the story gets almost comically ironic. The United States didn't produce enough titanium. The Soviet Union, however, was the world's leading titanium supplier. So the CIA secretly purchased Soviet titanium through shell companies, routing it through third countries. The Soviets were unknowingly providing the material for a spy plane specifically designed to watch them. But having the titanium was only the beginning. The metal presented manufacturing nightmares. Titanium reacts with chlorine, even the trace amounts in tap water. Parts exposed to chlorinated water during manufacturing would pass inspection, but corrode and fail months later. Workers had to use distilled water for everything. Traditional cadmium-plated tools caused embrittlement. The team developed entirely new tool coatings. Welding required inert gas chambers. Standard assembly techniques didn't work. Rivets had to be specially designed because normal expansion rates would cause structural failure during thermal cycles. Every lesson was learned through catastrophic failures. Test components cracked, welds failed, panels warped. Each setback cost time and money. But gradually, the Skunk Works team became the world's foremost experts in titanium fabrication. They weren't just building an airplane, they were inventing an entire manufacturing discipline. The final SR-71 contained over 13 miles of weld seams, each one perfect. Each one holding together at temperatures that would destroy conventional aircraft. Engineering madness, design features. The design of the SR-71 looked like something from another world. Long, sleek, predatory. The entire aircraft painted in a dark blue-black finish that earned it the name Blackbird. But every curve and surface served a purpose. The chined fuselage, those sharp, blended edges running from nose to wing, did multiple things. They generated additional lift at high speeds through compression lift. They helped manage shock waves. And they reduced radar cross-section decades before stealth became a design priority. The SR-71 wasn't technically a stealth aircraft, but its radar signature was surprisingly small for something so large. That black paint wasn't just for looks. It contained microscopic iron spheres that absorbed radar energy. The paint also helped radiate heat. At cruise speed, the airframe needed to shed enormous thermal energy, and the dark surface helped. The twin Pratt & Whitney J58 engines sat far out on the wings in elongated nacelles. These weren't normal jet engines. Above Mach 1.6, they transformed into ramjets. At cruise speed, the engines themselves produced only about 20% of thrust. The inlet cones moved back, creating carefully managed shockwaves that compressed incoming air. This compressed air generated most of the thrust through pure physics. No moving parts, just controlled supersonic airflow. Each inlet had to manage airflow precisely. Too much air caused unstable combustion. Too little caused inlet unstart. A violent pressure imbalance that jerked the aircraft sideways with 40,000 pounds of instant asymmetric force. Pilots described it as getting hit by a train. The inlet control system made hundreds of adjustments per second to prevent this. Now here's the truly bizarre part. The fuel tanks leaked on the ground. This wasn't a flaw, it was intentional design. Titanium expands significantly at high temperature. The tanks had panels fit loosely enough that they only sealed properly when the aircraft heated up to cruise temperature. So every SR-71 sat in a puddle of JP-7 fuel on the ground. Pilots took off with fuel streaming out, immediately rendezvoused with a tanker, refueled, then accelerated to mission speed, where the tanks finally sealed. Ground crews got so used to fuel puddles, they'd place drip pans underneath and joke about it. The fuel that wouldn't burn. Speaking of fuel, the JP-7 was another innovation born from extreme requirements. Standard jet fuel, JP-4 or JP-5, would ignite from friction alone at Mach 3 speeds. The fuel system would become a flying bomb. JP-7 had an extraordinarily high flash point. You literally couldn't light it with a match. Pilots demonstrated this at air shows. They'd pour JP-7 on the ground, throw a lit match at it, and the match would just go out. This stability was necessary because fuel circulated through the aircraft as coolant, absorbing heat from hydraulics and electronics before being burned. But this stability created another problem. How do you start engines with fuel that won't ignite? The solution was triethylborane, or TEB. This chemical ignites spontaneously on contact with air. Each engine had a limited supply, enough for 16 starts. Pilots had to track TEB usage carefully. Running out meant an engine that couldn't restart, which on certain missions could be fatal. The fuel system held 80,000 pounds of JP-7, more than the aircraft's empty weight. The fuel itself served as hydraulic fluid and coolant flowing through heat exchangers throughout the airframe. It was a closed-loop system where every gallon served multiple purposes before finally burning. The retirement controversy. The SR-71 was retired in 1998, officially replaced by satellites. The logic seemed sound. Satellites couldn't be shot down, covered global areas, and were becoming more sophisticated. But many argued then, and still argue now, that retirement was premature and strategically foolish. Satellites follow predictable orbits. Enemy nations know when American reconnaissance satellites pass overhead and can hide activities accordingly. The SR-71 could fly anywhere on hours' notice. It was unpredictable, flexible, and immediate. Satellites can't be tasked quickly for emerging crises. The SR-71 could be over any spot on Earth within hours. In fast-moving situations, that responsiveness was invaluable. There were also persistent rumors, never confirmed, never denied, about the SR-71's replacement. Aircraft like the hypothetical Aurora or other black projects. If such aircraft exist, they remain classified. What we know is that no acknowledged aircraft can match the SR-71's combination of speed, altitude, and reconnaissance capability. Some SR-71s were briefly brought out of retirement in the mid-1990s due to reconnaissance gaps, then retired again. Today, the surviving Blackbirds sit in museums, reminders of an era when the answer to every problem was to go faster. The SR-71 Blackbird represents a unique moment in aviation history. An aircraft so advanced that decades after retirement, it remains unmatched. A machine that required inventing new materials, new manufacturing processes, new fuels, and new ways of thinking about flight itself. It was speed made tangible. Not just fast, but impossibly, unreasonably, magnificently fast. Speed was life. And the Blackbird lived like nothing before or since. Thank you for watching. If you enjoyed this deep dive into engineering excellence, give it a thumbs up and share it with anyone who appreciates extraordinary machines. Subscribe and hit the bell for more stories of innovation and engineering marvels. Leave a comment telling us what aircraft or technology you want us to cover next.